Welcome back to Earth Science, everybody. This is Mr. Olson, aka the Bob Ross of Science. And our goal today is to continue where we left off with our rock cycle diagram the other day and complete the diagram today. So we started our diagram. We covered sedimentary rocks, and we talked about a lot of the processes that happen above ground to turn rock into another type of rock. We went through weathering, sediment, erosion, deposition, compaction, and cementation to create these different rock types. We're focusing in science this year, especially and every year, on vocabulary, learning vocabulary. This morning at a meeting we learned that students have to hear things and use a word on average 10 times in order to really learn the word. And I don't think I always do that. I don't think I'm saying weathering, erosion 10 times. So what I would say is this, as we're drawing our diagram, try to stay focused on what the words actually mean and how we're showing their meaning as we draw it. That's the reason why we're doing a diagram, so we can see it, we're showing it, we have an understanding of what these vocab words mean because we can see what's actually happening. And that's what I like about earth science. A lot of the things that we do are easy to visualize, easy to see. All right, so we went earlier and made a whole bunch of different sedimentary rock types: sandstone, shale, siltstone, limestone, conglomerate. What we're going to do next is we're going to move into the world of metamorphic rocks. And metamorphic rocks are rocks that have been changed by heat and pressure. Changed by heat and pressure. So as we go deeper and deeper into the earth, it's going to continue getting hotter. And there's going to be more and more pressure building up too. So we're going to put a little arrow here. And we'll say as we go deeper into the earth, there's increasing heat and pressure. So as we heat up these different rocks, and as we put them under pressure, we're going to see that they start to change. Heating them up is going to let them become partially melted. And the pressure is going to compact the rocks. It's going to sometimes smear mineral grains out. So for example, one time I bought a bag of those sour gummy worms. You know what I'm talking about? Ooh, they're so good. Yeah, but I left it in my car. Yeah, and they all melted kind of into one monstrous gummy tangle. And they kind of smeared out and gooed out. They weren't as good. But that happens to the minerals too. I'll show you. So for example, let's say we start out with the rock type conglomerate, sedimentary rock conglomerate. It's got pebbles and cobbles and sand, lots of cool things included. Well, if you metamorphose conglomerate, if you put it under heat and pressure, look what it forms. It forms what's called a metaconglomerate. You can see that it's been flattened, it's been smeared. I think this is a great picture because you can see that some of these minerals, some of the rocks that were in the conglomerate, you can tell they were melted. They were partly melted, kind of like taffy, and they got stretched and squished and flattened out under that heat and pressure. The whole texture of the rock changes. We could tell that the pressure was pushing down this way because the minerals flattened out to the sides, just like if you were to squish a ball of putty. So metamorphism's cool because it transforms the rocks. You get all kinds of neat textures and patterns that are forming, and you can see the details in the rock that show you it has been changed. So when we get down here deep in the earth, there's a lot of heat and pressure, and it affects the rocks. And it doesn't just affect a few rocks, it affects all the rocks. So for example, let's say you went to the Grand Canyon. and you were checking out all these different hundreds of sedimentary rock layers, eventually you'd get deep down enough and the sedimentary rocks would stop and you would have metamorphic rock that pretty much continued all through the Earth's crust for miles and miles. Virtually on any continent on Earth you could dig through sedimentary and volcanic rocks, and eventually you're going to hit metamorphic rocks that just continue down to depth. It's affected the entire region, the entire continent. Well, that type of metamorphism that affects a really broad region is called regional metamorphism. The symbol that we use to represent metamorphic rock is cool. We use a green color because some metamorphic minerals are green, like olivine, for example. And then we draw these kind of wavy layers of lines that show that the rocks have been folded and bent, twisted. It's hard to imagine taking a solid rock and flattening or stretching out the minerals like pulling taffy, or bending and twisting entire layers of rock. And if you wanted to see examples of metamorphic rock, a great place to go is to the mountains, because the mountains have been lifted up, and so rocks that used to be down deep are brought up to the surface. And the best place to see metamorphic rocks, I think, is a road cut. So here's what a road cut is. You have to cut the road through the rocks so that you can drive through. Instead of going up and over the mountain, you're kind of going through. Well, this is your chance to see some pretty cool metamorphic layers. And look at these rocks, how they've been bent and folded and twisted. Or look at these ones. They make incredibly twisted and bent shapes. Here's one where it's almost like a Z. And here's another really twisted and folded layer of rock. So you can see why we would use the symbol we drew for metamorphic rocks. It's realistic. Look at this one. So those rocks are partly melted. That allows them to bend and flex and twist. All right, so let's say that we continued heating those rocks and they actually melted all the way. That's going to bring us over here. So let's take a larger arrow, and we're going to say we're going to have some melting going on. What do we call melted rock that's inside the earth? What is it, Jack? What do we call melted rock inside the earth?
Magma.
Magma, thank you. We kind of drew a large bubble of magma. Coming up from down below. Now think about this. Have you ever toasted marshmallows? Yeah? Did you ever burn one up? It got a little too close to the heat, didn't it? It caught fire. Well, think about this. We have a magma body that's moving up through the earth, and there's layers and layers of other rock here. Well, the rock that's just sitting here right next to that 1400 degree magma, it's going to burn too. It's going to cook. So we have some more metamorphism that happens right here in this zone next to the magma. So we're going to shade that in and show that the rocks that were in contact with the magma have been metamorphosed. They've been affected by that intense heat. They got totally cooked. Now, if you've toasted marshmallows, you know you got to stay a little bit away from the fire if you want it to be perfect. If you back your marshmallow out, it's not going to get cooked as much. Well, the same thing holds true for the rocks that are a little farther away from the magma. They'll still metamorphose, but not as much. So we're going to shade those in lighter to show that they've partially metamorphosed, but not as intensely. And then, of course, if you held your marshmallow too far away, it wouldn't cook at all. You just have a boring, plain marshmallow. These rocks out here that are far enough away from the magma, they're not going to get changed at all. So we see kind of a zone of increasing metamorphism as we get closer to a magma body. When we started our diagram, we left a huge crater up here. That crater is going to be an impact crater from a giant asteroid. So let's draw an asteroid up here. Cruising down from space. When that asteroid hits the Earth, there will be so much energy, so much heat and pressure that that asteroid's probably going to vaporize. It doesn't just melt, it turns into vapor. And the rocks that are here that get hit with all that heat and pressure, they're going to metamorphose too. So let's draw, again, some heavy metamorphism happening right next to the surface. And less metamorphism a little bit deeper down. And then the rocks past that would be unaffected. This type of metamorphism is different. Excuse me. It didn't affect an entire region. Regional metamorphism affects, hundreds or thousands of miles worth of rock. But this type of metamorphism only affects the rocks that were touching the pressure or touching the heat. And so the word we use for this type of metamorphism is contact metamorphism. It had to be in direct contact with the heat and pressure. So contact metamorphism would apply to these rocks here by the magma, also the ones along the meteor crater. So tomorrow in class, we're going to break out some metamorphic rock samples. I have some pretty cool ones to show you guys. I've never been to a meteor crater, so I don't have any of that stuff, unfortunately. But yeah, we'll check out some of these. And we don't have a lot of vocab. You can see that there's a little bit. Heat and pressure is what's causing it. There's two main types of metamorphism. We've got regional, affecting a huge body of rock, and contact metamorphism that's affecting a smaller amount of rock. And of course, when we look at our metamorphic rocks, we'll be able to classify them a little bit further based on their texture, what they look like, but we'll save that for tomorrow. We've got one more type of rock to cover. Are you feeling comfortable with metamorphic so far? Yeah? Okay. So the last type of rock is igneous rock. And igneous rocks are really cool because they started out as melted magma. Let's show, we've got some open space here below our volcano. Let's say that from this large body of magma, there was a little bubble that rose up. You may call that, it might be called a pluton if it's very large. It might be called a pegmatite. Those aren't words you need to know, but they are cool words to know. Each branch of geology has its whole language. All right, so here's our smaller body of magma that rose up and started to rise. Well, we found with metamorphism that as you go deeper into the earth, there's increasing heat and pressure. So if we're coming back up towards the surface of the earth now, there's going to be less heat and pressure. And if it cools down enough, this magma could start to freeze. It could start to crystallize. So we're going to show that. We're going to show that floating in this magma, some minerals started to crystallize. So the symbol for this type of rock, where magma cools inside the ground, you have kind of like randomly oriented crystals. I'm going to start by drawing a secret smiley face inside mine. Very happy little character. And then we can just fill it in. It's randomly oriented crystals. They're floating, so they kind of grow in all directions. One crystal is going to grow until it touches the next crystal. You would be able to see the crystals. And this is igneous rock that is formed inside the earth. We saw this in a gizmo that we did the other day. Does anybody remember the name for igneous rocks that form inside the earth?
Oh, it was something intrusive.
Ah, very good. Intrusive. Nice work. Intrusive igneous rocks. That prefix in tells us right away that's where it's forming. And intrusive. Igneous rock. Also, if you think about the word intrude or an intruder, that's something that forces its way in, right? And this magma forced its way into the other rocks around it. It intruded in there. So that's a couple ways to help remember intrusive igneous rock. Since the magma cools down slowly, there's a lot of time for crystals to grow. So you can get some very large crystals in the intrusive igneous rock. Would we have any gas bubbles in this intrusive rock? It's under pressure. The magma is under a lot of pressure. So if there were gases in the magma, they wouldn't be expanded enough to see. So those gases would stay kind of like dissolved in the rock. So we would see no gas bubbles in an intrusive igneous rock. And we would see like a coarse-grained or large crystal texture. All right, so that covers intrusive. We'd see like granite and gabbro. Those are the two examples we saw with our virtual lab the other day. All right, let's bring some of this magma all the way up to the surface. So we're going to hook up a vent here, all the way up to the top. And of course, it's not that simple. A volcano is going to have a really cool plumbing system inside where there's like little side branches. We can have some of these. There are different types of volcanoes too, like 3 main different types. And some volcanoes are made really out of loose rocks. It's almost like a pile of cat litter. It's a bunch of little specks of lava that shot out and hardened in the air and then just rained down on the slopes. So really it's not held together very well. A lot of these volcanoes aren't really very solid. And if it's kind of loose like that, sometimes lava can actually just flow through the pile. It doesn't have to erupt out the top. It could erupt right here through one of these side channels. So let's take a lava flow and fill in this space. This is lava. It's different from magma because it's outside the earth or close to the surface. Still melted rock. So compared with our magma that cooled down inside the earth, the intrusive rock, is this lava going to cool down faster or slower, do you think?
Faster.
Yeah, a lot faster. Let's show that. So I'm just going to shade it in a little bit darker here to show that it's starting to cool and harden. Since it cools faster, we wouldn't really see much for crystals. We wouldn't see big crystals that we could point to. It would be very fine-grained. And also, since it's kind of released from pressure, a lot of times those gases that are in there are going to expand, and you're going to have visible bubbles inside these rocks. So we had intrusive igneous rock forming inside the Earth. And I'm pretty sure I already heard somebody say, what's the term for this igneous rock that forms outside the Earth? Extrusive is right. Yes, extrusive. Nice. And we said that the word intrude means to sort of force your way in. And the word extrude is when you push something out. So if you squeeze toothpaste out of your tube, you're extruding your toothpaste. Or if you ever had one of those like Play-Doh pasta making machines where you shove in the wad of Play-Doh and you choose the shape and you push down and it squeezes out the tube. Oh yeah. And our town has a lot of manufacturing industries where they will extrude metal. You can actually take like a bar of aluminum and push it through a die and it comes out in the shape. And then the cut slices off and then you have a part for a machine. So that's extrusion is a process, of squeezing something out. So that makes sense too with our definition. We're very close to being done. I'd like to show a couple more things that might happen with this volcano, though. So of course, we would get maybe a big cloud of ash coming out. Volcanic ash is kind of crazy. It tends to be super fine. The particles would be almost like a dust or a powder. It might look like flour, that consistency of flour, very small particles. But if you were to look at volcanic ash under a microscope, look at it. What's it look like?
Glass.
It is glass, yeah, because think about if you've ever blown a bubble, like a soap bubble or a bubble of gum, and then it pops. No big deal because it's, gummy or liquid stuff. Well, when the volcano erupts, it's blowing bubbles of rock. And think about obsidian, volcanic glass. It's basically blowing little glass bubbles with gas inside, and the gas is pressurized. So as soon as those like bubbles of lava shoot out and harden, they shatter because they're pressurized. And the shattered pieces are very sharp, very sharp. This makes volcanic ash very dangerous to breathe in. It's a severe health risk. If you breathed in little particles of glass, you can imagine it would cut your lungs. But also, volcanic ash, when it mixes with water, it gets really heavy and dense like concrete. And so you would basically, if you're breathing in volcanic ash, you basically would have your lungs coated with concrete. It's deadly. So what we would want to show in our volcanic ash cloud, I'm going to put in a bunch of little curved pieces to show that volcanic ash, even though it's microscopic, it's very sharp, it's jagged, it's dangerous stuff. Sometimes an airplane will fly through a cloud of volcanic ash, and the ash gets into the engine and fuses into just like glass. There have been a couple cases where planes almost crashed after flying through a volcanic ash cloud. So there's your ash. Pretty gnarly stuff. We saw a video too where a volcano shot out what's called a volcanic bomb. The volcanic bombs are cool too because it shoots out as a blob of lava, and as it's moving through the air, it becomes tapered and streamlined. It's kind of shaped like a football. And those can range from the size of like an almond all the way up to maybe roughly the size of a small car. So there's our volcanic bomb. All right, so the rock cycle diagram is complete. How do you feel about the vocab we learned? How do you feel? Do you feel comfortable with it?
It doesn't seem too long.
It's not too bad, is it? We'll want to make sure we keep using these words whenever we can. So if we're talking about this, we want to make sure that we're using the words that we learned. And of course, we've seen it, we've said it. It's time to write some of the vocab down. So you will take out your rock cycle vocabulary. We're going to add some metamorphic vocab today. Our first vocab words, metamorphic rock. Rock that has been changed by heat, pressure, or the introduction of chemical fluids. So if you had superheated groundwater moving into some fractured rock and it was carrying new minerals with it, you could have rocks that change. You've added new ingredients. Under heat and pressure, the minerals can rearrange themselves too. And metamorphic rock is where we find a lot of our gemstones. We saw in our TV program that rubies form in metamorphic rock. The minerals are able to move around, the atoms can reconfigure and form really cool gems. So metamorphics are cool for that reason too. We talked about two different kinds of metamorphism. You could have contact metamorphism where rock has been transformed through direct contact with heat or pressure. Good examples would be coming into contact with a body of magma or an impact crater. Contact metamorphism usually only affects a small amount of rock. Probably much more common is going to be our regional metamorphism, where we have like an entire body of rock that was changed by heat and pressure. So deep within the earth, and over long periods of time, we have whole plates of the earth that crash together, and they will fold and bend and buckle the rocks into all kinds of bends and folds. And we have just 2 more terms, ways to describe metamorphic rocks. You'll see these tomorrow. Tomorrow, you'll need to know these last 2 words to help identify the different rocks we're looking at or describe their texture. And the first one is foliated metamorphic rocks. Foliated metamorphic rocks have layers, and sometimes they'll have bands of color. Have you ever heard of exfoliation? Like maybe a beauty product that exfoliates your skin? Have you? Yeah? What's it mean, Autumn? What does exfoliate mean? What's happening? Anybody know? If you're using some sort of exfoliating product, you're trying to, yeah, you're trying to remove dead layers of skin, right? And get down to the fresh, beautiful, glowing, healthy skin underneath, right? Well, that word foliated, it means layers, kind of. It means like leaf or a sheet. So the word foliage, here's foliage, leaves, lots of layers of leaves. If you have a very early publication, like before there were actual books, they would be called a folio. So like Shakespeare's first poems and plays were published in a folio, a loosely collected, leaves together. And if you could carry it with you, you might call it a portfolio. So that prefix foli, it means kind of like leaves or sheets. So our foliated metamorphic rocks, you'll be able to see sheets of minerals. A lot of times different colors like black, white bands. And then non-foliated, they're rocks that don't have layers in them. Oftentimes the minerals there are going to recrystallize and become smoother and more uniform. So we'll see a couple really cool rocks that are non-foliated too. All right, well that concludes the metamorphic vocab. We'll work on igneous vocab tomorrow. We have just a couple more to do there. But that is the end of our lesson today. Have a great day.